Welcome everyone. Hope you all are doing well. Today, let's discuss about the star delta conversion in a DC circuit. Now, hope you all know the current division rule in a DC circuit. Just to recall that, let's do it another time. Let's consider this as a circuit having two resistances connected in parallel, R1 and R2. Now, due to this voltage source, a current I is going through the circuit, and that is getting divided into I1 and I2. Now, what will be the magnitude of these two currents? To find that out, we need to first mm, implement the current division, that is the supply current, which is I, getting subdivided into I1 and I2. So we have written the equation as I equals to I1 and I2. Now, for the division process, we are implementing this I2 as I1 multiplied by the first resistance divided by the second resistance, or the nearest by furthest, right? Now, in the next step, what we are doing is we are taking this I1 as common, and um, we are making an equation, or making a relationship uh, of I1 and I, or the supply current. So this relationship is necessary, and this is the multiplying factor, or the division factor by which we can the decide that how current will be divided in these two resistances. Now, there is a simple way to remember this. Uh, we can say that if we are calculating the current through the resistance R1, which is I1, then we take the supply current and we multiply that to the furthest resistance, which is R2, by the summation of the total resistance in the circuit, and this resistance also includes the internal resistance of the circuit also. If it is required for any circuit to consider the internal resistance, we have to consider the internal resistance also. Now, for I2, the same thing, that I2 is the current through R2, and from R2 the furthest resistance is R1, right? So we take R1 as the resistance as the numerator and divide that by the total resistance in the circuit. That will give us the division factor for I2, right? Now, let's come to the second slide, where we will see the voltage division rule. Now, voltage division rule applies for only the resistance which is connected in parallel, and similarly for the previous circuit. Uh, so here we can see there is a voltage source similar to the previous one, and the resistance R1 and R2, which are connected in series, right? So in series, the voltage get subdivided, or voltage division happens, and in parallel, current division happens, voltage remains the same. Now here also, what we will do, we will form an equation for the voltage. So the voltage drop across R1 is V1 and the voltage drop across R2 is V2, right? So we can easily form this equation that V equals to V1 plus V2. Now, let's take this V2 or convert this V2 with respect to V1. How we can do that? We can do that by the furthest resistance by the nearest resistance or the self resistance, right? So V1 multiplied by R2 by R1. So this also gives the division factor, that is R1 by R1 plus R2, which is same as the previous one for the current division rule. Is it the same? No, is it not? It's not same. Here we are taking the self resistance by the summation of resistance. Here we are taking the self resistance, which is R1 in the previous one, that is R2, right? In the next case, or in the voltage division rule, we will be taking the self resistance by the summation of total resistance. Now this becomes the division factor for the voltage division rule, and this also happens over here, division factor. So easy way to remember that current division rule for I, we are going to take furthest by total, and for V we are going to take nearest or self by total. These are all resistances, right? And as this is a division factor, this division factor has no units, so these ohm and ohm will cancel out, right? Let's get into the point. Now here we can see the typical diagram for a star connection and a delta connection. Now we can see that in star connection there's only the representation of resistance is only Ra, because it is connected to a neutral terminal, so no other terminals are affected by it, so only Ra. Similarly in this case Rc, similarly in this case Rb. But for delta connection, this one, the connection is between two phases, right? A and C. So the phase A and phase C has its effect on this resistance, so it is represented by RCA. Similarly for that, we represent this as RVC and RAB. Those who have effect, we have we are uh, taking this suffix on the basis of the phases that these resistance connects. Uh, Now moving on, we see how these two connections are interrelated with each other. Now this is a typical formula to convert a star connection to a delta connection and a delta connection to star connection, vice versa. So let's see how this is done, or easiest way to remember this. So in this case, we are seeing this RA, RC and RB. Now we have to convert this RA in terms of R1, R2 and R3, to so that this star connection becomes a delta, right? So that it becomes a delta. So how can we convert this with respect to delta? Now for this one we need this formula. So this one needs this formula. Now to convert this R1, we are going to get RA RB plus RB RC plus RC RA. Now let's see how to remember this properly. Now R1, here we can see R1 is connected between A and C. right, is connected between A and C. So the missing one, the missing phase is phase B, right? So we are taking the denominator as RB, right? And every other possible combinations of resistances in terms of 2, we are getting the summation of that as a numerator. So how can we do that? So AB, AC and BC. These are the three possible combinations of the resistances. So RAB plus RBC plus RCA, right? These are similar for all the cases. For R2 it is same, for R3 it is also same. So the only change that is going to happen, the missing phase. So the keyword that is to remember to convert this delta into a star is missing phase as denominator, right? So missing phase as denominator. Here we can see that for R2, R2 is connected between R2 is connected between A and B. So the missing phase is C. So here at the denominator we write C, RC, right? Similarly for in this case R3. So R3 is connected between between C and B. So the missing phase is A. So we are taking it as RA, and the numerators are all same. So you need to remember only the numerator and the denominator will come by as we see the circuit. Right? Now coming to this connection, where we have to convert this we have to convert this mm, delta into a star. So we are given the values of R1, R2 and R3, R1, R2 and R3, and we have to convert this delta into a star so that we can get RA, RB and RC from these three values R1, R2 and R3. So how to do that? So now here the trick is also quite similar, but a little bit different. Now RA, RA is connected only A, right? Now here A has two connections with C and with B, right? A has two connections, it is only A. So A has two connections with C and with B. So the numerator will be the multiplication of the resistance between AC and AB. So R1 and R2. So here you can see that RA, which has the numerator of R1 and R2, right? And the denominator is the summation of all the resistances R1, R2 and R3, right? Now for B, let's see whether this is correct or not. So this B has a connection with A and as well as C. So the resistance between B and A is R2 and the resistance between B and C is R3. So R2 and R3 goes in the numerator and the denominator is as always same. Now in case of RC, let's look into this whether this is also same or not. RC, you can say this C which is connected to A and B. C and A, the resistance between them is R1 and C and B, the resistance between them is R3. So R1 and R3, right? So this is the easiest way to remember. Now let's talk about some of the advantages of star delta conversion. Now the primary side is star connected. Obviously if you are connecting doing a star delta conversion, the primary side is always connected in star. So hence fewer number of turns are required, that makes the connection economical. So Connection, fewer number of turns means lesser number of coils. That means economical structure design or economical equipment design. The second point is uh, the neutral available on the primary can be earthed to avoid distortion. So the neutral which is available in the primary, so this point is a neutral position which is available in the primary can be earthed. This point can be earthed accordingly to avoid any kind of distortion in the circuit. Now, the third point is large unbalanced loads can be handled satisfactorily. Now, what an unbalanced load? Unbalanced load is if the circuit does not have a proper distribution of load in its edges. So we will talk about that later, but it the primary side if connected in star, it also helps in unbalanced load in the secondary side, right? So now let's talk about an example with an example. Now let's see that this is a circuit. This circuit comes in examinations many times, and to solve this, it is pretty difficult to solve, right? So which one is parallel, which one is series, is quite difficult to remember. So here we can see a shape of delta, right? This is the shape of delta, and it has already been denoted by A, B, and C. So now we can convert this delta, or we can convert this to the lower part. We can convert this to. So if we convert this delta into a star, so this is our AB, this is our CB or BC, and this is our mm, AC, right? Right. Sorry. Now here we wrote it as R1, we wrote it as R2. Here from here we can see this is R1, this is R2, and this is R3. So we are writing this as R1, R2, and R3, right? So here we see that we have to find the value of RA, RB, and RC. So the this equation will be necessary for it, right? So now we can say RA, the conductors or the resistances that connect A with B and C, right? So 10 multiplied by 5 divided by the total number of resistance, which is 10 plus 10 plus 5. Oh, this is RA. Let's see RB. RB connects this B connects A and C. So we will take 5 and 10. So 10 multiplied by 5 again by 10 plus 10 plus 5. Oh, and here C connects A and B. So RC will be 10 multiplied by 10 divided by 10 plus 10 plus 5 ohm. So this is the conversion of this delta into a star. So how will it look like after the conversion? So this is the resistance of 9 ohm over here, and we have performed a conversion over here, and now we have the circuit resistances like this, and this completes the circuit. Now this is RA, right? So RA will be having this value. So this is RA. This is RB. So RB will be having this value. And this is RC, which will be having this value, right? Now here we have got 8 ohm resistance, and here we have got 4 ohm resistance. So after calculation, we can see that this RA value becomes 2, this RB value becomes 2 again, which we have seen RA and RB values are same. RA values and RB values are same. Now we can see that RA and RB are same here, and RC having a different value, and this is the complete circuit. Now solving this circuit is quite easy because this portion of the circuit we can consider it as a series circuit. This portion of the circuit we can consider as a series circuit again. So this will give us a simple series parallel circuit having only these two resistances. This is 2 ohm, this is 2 plus 4, 6 ohm, and this is 4 plus 8, 12 ohms. So this is 12 ohms, this is 9 ohms, and this is the whole. Now we can perform the series parallel operation in this circuit to easily get the answer, which is 15 ohm, right? So star delta transformation, star delta transformation is also easy. Star delta transformation, we have seen the formulations previously, and we are not going to discuss this again. This is quite the same. So what are the features of this star delta star conversion? So the secondary is star, which means the secondary phase voltage is 1 by root 3 times of the line voltage. The neutral in secondary can be grounded. That means again the same as the previous one. The neutral in the secondary can be grounded in three-phase four-wire system. Neutral shifting and third harmonics are there. Now, what is neutral shifting? No need to know. You don't have it in the syllabus. Just know that neutral shifting reduces third harmonics. Phase shift of 30° between secondary and primary current voltage because of this 1 by root 3 condition, right? So these are some of the features of the delta star conversion, and now in the conclusion we can say that the three-phase AC systems are considered as a balanced circuit made up of a balanced three-phase source, a balanced line, and a balanced three-phase load. Secondly, the star delta or delta star conversion is required in a three-phase AC system to simplify the circuit and ease their analysis. And thirdly, if a three-phase supply or a three-phase load is connected in delta, it can be transformed into an equivalent star-connected supply or load. After the analysis, the results are converted back into the original delta equivalent. So the conversion becomes much more easier, load balancing becomes much more easier, and this consideration can also be done in DC circuit as well as AC circuit. Sorry, DC circuit will not be applicable, only in AC circuit because three phase is only available in DC systems. But the conversion performance that we have done in the example, the conversion can be used, the conversion procedure can be used in case of DC circuit also, right? So phase conversion is not applicable in DC systems, but conversion for the equivalent resistance required can be done in DC circuits also. So that's all for today. Stay safe, stay at home, study. That's it. Thank you.